Let's talk about Newton's method for finding zeros of functions and for solving equations. The method itself is a faster way to find zeros of functions because, well, we have already seen that if we want to find zeros of functions, we have the bisection method, right? However, the bisection method takes a long time, right? Every bisection only cuts the length of the interval in half, and that means it takes a long time until you get 4 or 5 significant digits that are actually accurate. So, because computational speed will always be important, a faster method will always be useful. I know that computational speed has increased tremendously within my lifetime and probably even also within your lifetime. However, just because we've got a lot of computational power available does not mean that we ought to waste it. People who run numerical algorithms on supercomputers have a lot of computational power available, and they are not running the bisection method because it wastes time. So Newton's method is one such method that achieves the same goal. It finds zeros of functions and solutions of equations, but it does so faster. Let's take a look at what it does. Well, let's remember first of all the underlying idea of numerical analysis. You always replace the problem with a simpler one. And so if our original problem is to solve the equation f of x equals 0, well, that's hard because for nonlinear functions that may not be possible to solve at all by hand. But if we replace that with finding the zeros of a tangent line, well, finding zeros of straight lines is easy. So the question now is just how do we replace finding the zero of this function, so finding the zero right here, with finding the zero of a tangent line? Well, we start at a point that is somewhere near the zero. It certainly is not where the function is equal to 0. And we find the point where the function is at that place, and we find the tangent line at that point. Well, the zero of that tangent line we can compute. No problem. What we can see in the picture is this 0 is closer to the actual 0 of the function, but it is not equal to that. Okay, but so basically that means if we just find the 0 of the tangent line, we got closer. Nothing forbids us from repeating this process. So let's take the point x1 equals b. We go to where the function is at. We find the tangent line. We find the 0 of the tangent line, and we can see we've gotten even closer. All right, mark that point x2. Go to where the function is at. Find the tangent line, find the 0 of the tangent line, and we can see this has gotten really close, and I think we can also imagine that this process now will produce values that are closer and closer to the actual 0 of the function. And that is how Newton's method ideally works. Now, of course, what we need to do is we need to turn these pictures into formulas because ultimately we want to compute, and I can't just show this picture to a computer and say, this is what you're supposed to do, now go ahead and do it. So first thing we need is the 0 of the tangent line of the function f at a point A. Well, the equation of the tangent line at A is one of those equations that I don't really have memorized, but what do I know? I know that the slope of the tangent line is f prime at A. I know that at A, it's supposed to have the value f of A, which it does when we have an x minus A here. So this is a line that has slope f prime of A, and which is equal to f of A at A, and that means it's got to be the tangent line. Solving this thing for x is routine, right? First we multiply out the parentheses, then we bring everything but the term with x over to the right side, so we get f prime of A times x is equal to f prime of A times A minus f of A, and we divide by f prime of A, and then if we simplify we end up with x being A minus f of A divided by f prime of A. And so now the definition of Newton's method is that if we have a differentiable function and x0 is a point in the domain of that differentiable function, then Newton's method, started at x0, generates the recursive sequence that is defined by xn plus 1, the next point in the recursion, is equal to xn minus f of xn divided by f prime of xn. And from the previous panel we know that this right-hand side is just the 0 of the tangent line of the function at xn, so it's the 0 of the tangent line at the previous point. And the recursion then is that every next point is generated as the 0 of the tangent line at the previous point. Okay, so here's the visualization again. We start with x0, we compute the tangent line, take that 0, compute the tangent line at that 0, compute the tangent line at that 0, and that process apparently moves us closer and closer to the 0 of the function. So Newton's method generates a recursive sequence that is a new concept for us, most likely. That is something that is sometimes a little bit of a hiccup in class, even though it shouldn't be, because the idea isn't that hard. The idea for a recursive sequence is that you've got a certain recurrence relation, which for us is this formula that generates the next number from the previous number in a certain way. And that recurrence relation basically is a black box, and what happens is you feed your x0 in there, you get an x1 out. Then you feed that x1 back in, and you get an x2. You feed that x2 back in, you get an x3, and it just continues like that. Let's finally look at an example with numbers. So what could I ask you on a homework problem? Well, I could ask you to find the zeros of f of x equals x cubed minus 5x plus 5, which technically we could still use the cubic formula on. It's not a quadratic, it's a cube here, right? But we could technically use the cubic formula on that, but that cubic formula is horrible, so typically we use numericals on something like that. Here's the function. First thing you want to do is get a picture, and that function has a 0 near x equals negative 3. So we might as well start at x0 equals negative 3. That's how we get the starting points. If it isn't a total random guess, or if it isn't given, then just graph it and take something that's near the 0. Okay, so the function is x cubed minus 5x plus 5. That means the derivative is 3x squared minus 5. That means if our recurrence relation is xn plus 1 equals xn minus f of xn divided by f prime of xn, then that would be xn minus f of xn is xn cubed minus 5xn plus 5, and f of xn prime is 3xn squared minus 5. How do we use that? Well, x0 is negative 3, and that's chosen near the 0. x1 is just x0 plugged into this big old horrible formula, which means we just plug in negative 3 here. And now let's see if I can figure this out. Negative 3 squared is 9 times 3 is 27 minus 5 is 22 in the denominator. And negative 3 cubed is negative 27 plus 15 plus 5, so negative 27 plus 7 is negative 7, so this is negative 7 over 22. And negative 3 is negative 66 over 22. We've got minus minus, so this is negative 66 over 22 plus 7 over 22 should be negative 59 over 22. Well, okay, here's the intermediate step, and here's negative 59 over 22. Hey, I can still work with fractions, and even though that one is a little bit on the hairy side, you want to be able to work with numbers and keep track of these things like that. Of course, if it doesn't want to work out, and in the next step it isn't going to, of course what we're going to do is we're going to use a calculator. Because now in the next step, well, we have to find x2 by plugging x1 into that same big old ugly formula. And that means that x1 is replaced by negative 59 over 22 in every single instance in which we have an x1, right? And that, computing that by hand certainly is cruel and unusual punishment, and so I just say ... here, use a calculator or a computer. That is something, if you have to execute more than 1 or 2 steps with Newton's method, that is a must. It's just that this panel shows that there's no mystery in how these numbers that we're going to see in the following problems, how these numbers are created. It's always, you take a number, plug it into the formula, take what you get out of the formula, plug it back into the formula, and repeat that. Just like on that panel with that repeating black box. And so what we get is, from this recursion, we get x0 is negative 3, x1 is negative 2.68181818, and that should also be a 18, that's just rounded, right? Then we get negative 2.62879 and then some. Then we get negative 2.6273 and then some. And here we're starting to see something because, well, the 2.6 stayed stable, the 2 is staying stable, the 736 apparently is staying stable, and in the fifth step, all the digits are staying stable. So that means now, unless there's something seriously wrong with my computer and there really wasn't going to make those slides, this number will keep repeating. So that means after 5 steps, Newton's method is stable, and we have found, let's see, 2, 4, 6, 8, 10, 11 valid digits behind the decimal point. Compare that with what happens in the bisection method. If we start with the bisection method with an interval of length 1, 5 steps don't even guarantee 2 accurate digits. So if we had used the bisection method, we would still be sitting somewhere around here. I don't think even we'd have the 2.62. I think we would be somewhere at the 2.6, and the rest would still not be reliable. So this is the reason why people like to use Newton's method. It really is very, very fast. Now, in mathematics, we also have to be careful with the various pathologies, and so, for example, Newton's method can get stuck. And so if we're looking at the same function that we have looked at, let me rewind that real quick. That is, if I remember correctly, the animation is set up with exactly the same function as what we just had in the previous example. And in the previous example, we had seen that this minimum here is almost but not quite 0. And so now let's see what happens if we start Newton's method at x equals 2. Well, then this animation shows that we keep computing tangent lines that keep having zeros near 2, and we're not getting anywhere near 0. The thing is just stuck. This can technically happen, in theory, happen indefinitely, but it can also happen, and this is what we've seen here, that at some point in time, your tangent line, oh, that was a good click, because we're exactly at the crucial point of the presentation. Some 0 of a tangent line may, no, that's still a bad 0. Let's keep going here. Okay, they're still stuck, still stuck, still stuck. But here now we computed a 0 of a tangent line where the slope is very, very flat, and that means our point has been shot out all the way to the left. And once it's been shot out that far, now we are in a situation like we had before, where Newton's method very quickly converges. And so Newton's method, because it isn't guaranteed, well, okay, there are theorems that guarantee convergence under certain conditions, but these theorems are very, very technical. If you just start Newton's method randomly at some point in space, it could happen that Newton's method gets stuck, and we certainly need to be aware of that, so that if you just get digits that don't stabilize, you realize you just have to reset your starting point. What else can happen? Well, if we applied Newton's method to the function f of x equals x plus 7, x and x minus 1, with x0 equals 0.5, well, first of all, we wouldn't need to apply it here, right, because we can read off the zeros, but this is an example. Well, if we do this, we would expect Newton's method to converge to 0 or 1, right, because these are zeros, and we're starting right in between. But x1 is negative 7, and that's kind of strange. You can verify the computation, or you can just look at the picture. Here's 0, here's 1, here's 1/2, and the tangent line is very flat and actually hits the x-axis exactly at x1 equals negative 7. Now that is something that I certainly set up to work out just this way, to demonstrate that Newton's method also need not necessarily find the 0 that is nearest to your input. So if you've got multiple zeros, you may have to have multiple restarts, and some of the restarts may just give you a 0 that you didn't quite expect at that stage. However, on the positive side, if we have a function f with continuous first derivative f prime, and if the sequence generated by Newton's method converges to a limit so that the derivative at that limit is not 0, then it is guaranteed that that limit actually is a 0 of the function, and the proof is fairly simple. You take this recurrence relation, xn plus 1 equals xn minus f of xn divided by f prime of xn, and you can take the limit on both sides, right? And whether I take the limit of xn plus 1 or the limit of xn, I will get the limit L. I just get there one step faster, which as we go to infinity doesn't matter that much. And the limit of xn is xn, the limit of f of xn is f of L, and the limit of f prime of xn is f prime of L. here's where we need that f prime of L is not equal to 0, otherwise we'd be dividing by 0, right? And if we now solve that, we realize the L's cancel, and if we then multiply the negative f prime of L over everything cancel, we just end up with f of L equals 0. Okay, so sometimes we can also use Newton's method for equations, and there's really only one trick to remember, and that is if you've got an equation left-hand side equals right-hand side, that's the same as left side minus right side equals 0, and the solutions therefore are the zeros of this function left side minus right side. So for example, if we want to solve the equation e to the x equals negative x, well, here's e to the x, here is minus x, the 0 is somewhere around negative 0.5, a little bit to the left of that. And we could therefore start at x0 equals 0, say. And what we have is e to the x equals negative x. That means e to the x plus x is equal to 0. That means we set the function equal to f of x equals e to the x plus x. The derivative would be e to the x plus 1. And that means that the recurrence relation is that the next number, xn plus 1, is generated from the previous number which is xn, by taking xn minus e to the xn plus xn divided by e to the xn plus 1, right? Function divided by the derivative. And if we start at 0, and I've used a computer here, well, okay, I didn't use a computer to choose 0, we did that on the previous panel. But if I use a computer, then x1 is negative 0.5, x2 is negative 0.566, x3 is negative 0.567, and then some. And then we can see here again, as Newton's method rapidly converges, a lot of digits are already stable in the step from x3 to x4. And by the time we go from x4 to x5, all the digits are stable, and that means Newton's method has converged, and we are at a0. Now technically you still want to take this number, plug it into f to verify that this is really close to 0. It'll probably give you something like 10 to the negative 13 or so as an answer because of rounding errors and the like. And so that would then verify that that really is a 0 of that function. Okay, so finally, as I'm also always pushing in this course, we want to take a look at what happens when we work with parameters, because that prepares us for multivariable calculus as well as for more realistic tasks. And Newton's method, for example, can be used to design an algorithm that computes the nth root of a number a greater than 0. Well, actually I'm going to compute the square root, not the nth root, right? Okay, so let me fix that real quick. Okay, now it is the square root. Let's reset here and let's do this over again. Well, basically the square root of a is the solution of the equation x equals square root a. Well, that means x squared is equal to a, because I don't want to have square roots in the computation, right? I can't just bring the square root over and then take derivatives, because it doesn't make sense to set up an algorithm that uses square roots to compute square roots. And so I set up x squared equals a. X squared minus a equals 0 is the corresponding equation. And that means, yeah, that was the standard trick, and that means that the recurrence relation is xn plus 1 equals xn minus f of xn, which is x squared minus a, divided by f prime of xn, which is the 2xn. And so now here the trick really is we have an algorithm that computes square roots without needing to know what the square root is, right? That is the big thing in numerical analysis. You have to replace the problem with something that you don't know how to solve yet. And, well, then we can simplify that a little bit. We can realize that the xn stays, xn squared minus 2 divided by 2xn is xn over 2, and a over 2xn stays the same. And so that then is xn plus 1 equals xn over 2 plus a over 2xn. And that is an algorithm that pretty quickly and reliably computes square roots. I am not sure if that is the algorithm that is implemented on your calculator, but similar algorithms really are implemented in operating systems to compute square roots because, well, I mean, a computer doesn't understand what a square root means. It needs some method to execute, and Newton's method works rather well for that. All right, in terms of what you can do in this section, well, there will certainly be problems where you have to just set up and work out Newton's method. Remember, you just set up your recurrence relation and then you just keep feeding the numbers back into the equation until they stabilize. And then there probably are a couple of problems where I want you to investigate various pathologies where you have a horizontal tangent line, which means Newton's method doesn't start, or that you set up a more general algorithm, such as potentially one where you find the nth root, because that is something that goes very similar to what we did on this panel, only that you work with x to the n. Anyway, this is it for this presentation. Sorry about the little hiccup with the nth root. And yeah, we move on.